Good morning, friends and dear students. I feel immense pleasure to be here again for my favorite course, flight mechanics. Also, it is known as aircraft performance. It is for the fourth semester aeronautical engineering students of Institute of Aeronautical Engineering, Hyderabad, India. I am Dr. Yagya Dutta Dwivedi, professor from Institute of Aeronautical, Department of Aeronautical Engineering, Hyderabad, India. Today my topic is derivation of thrust required and the minimum drag speed. In today's overview, it is revision of the drag polar, minimum drag velocity when alpha t, that is thrust angle, is 0, relation of CL and the CD naught for maximum CL, maximum coefficient of lift, minimum drag speed, power required to maintain steady level flight. These are my topic. I will be discussing about revision of drag polar, which I have already taken, but further it is required to understand what is the drag polar. We know that CD is equal to CD naught plus KCL square, where K is equal to 1 by pi aspect ratio E. Now, if you see that parabolic polar, if you see here, it is a parabolic equation. So here it is the CD naught it is the CD naught, and it is KCL square. It is the induced drag, and this is the parasitic drag. So the actual polar, it is the ideal polar, but in the actual polar diagram will be like this. It is not whole, it is from here, it is starting and it is falling down, and after this is your polar, but after this will fall like this. CL will fall at certain angle of attack. So here this is the CD naught and this is the CL at CD minimum. CD minimum is different here than the CD naught. CD naught alpha CL is equal to 0. So in this, at the CD naught where CL is equal to 0. Here is a KCL square, here is the CD naught. So there is a little difference between the actual polar, drag polar, and the parabolic polar. This you can compare here, and this is happening due to the stall. Stall speed, all of a sudden lift is not increasing but drag start falling. So generalized parabolic polar, we can see here that CD is equal to CD naught minimum plus K CL minus CD ideal whole square, where CL ideal is equal to CL at CD minimum. CL ideal is CL at CD minimum. That ideal lift coefficient, that is CL at the angle of attack of minimum CD. So this you can see in this diagram, CD at minimum CL. This is the CD here. This is shown in this diagram. Now we will see the minimum drag velocity when alpha t is equal to 0. This is the aircraft which is flying with a thrust TR. This is your velocity V. Lift is perpendicular to this, it is drag, and this is the weight which is always acting towards the earth. So minimum drag speed VMD can be written as V minimum drag is equal to under root W by SW by rho 4 by CD naught by E aspect ratio to the power 1 by 4 when alpha t is 0. For steady and level flight of the aircraft, see in this figure, D is equal to TR cos alpha t. So D is equal to this will be equal to this. Here it is TR cos alpha t, and this L is equal to W minus TR sin alpha t. So this W minus TR, one component will be here, that is TR sin alpha t. So we can write this TR is equal to W by L by D cos alpha T plus sin alpha T. So this L by D maximum will be here. So this is the L by D maximum, and this is the your velocity V, where we get the maximum L by D. To minimize the TR, we have to reduce the weight W or increase the L by D or both. So how to maximize L by D? Next slide, we will see how to maximize the L by D. So relation of CL and the CD naught for the maximum CL. We know that maximum L by D or CL by CD. So L by D half rho V square SW CL divided by half rho V square SW into CD. So this is cancelled. So CL by CD. So CL by CD, for CD we can write the CD naught plus CD naught L into CL plus CL square pi E aspect ratio. Here this CD naught L is this, because for this at zero angle of attack you will produce some lift. This is the CL and there will be some drag. So it is the CD naught into CL. It is for the cambered airfoil. Okay. So to have the maximum, this value, this DCL by CD should be differentiated with respect to the CL here. So if we differentiate this CD naught plus CD naught L into CL plus CL square by pi E aspect ratio into CL is equal to 1. Differentiation of CL is equal to 1 minus CL, and if you differentiate this, CD is equal to 0. Here is the CL, you will get CD naught into L plus 2CL by pi E aspect ratio divided by this denominator whole square is equal to 0. So this will become 0 here. So now CD naught plus CD naught L into CL plus CL square by pi E aspect ratio is equal to CL into CD naught L plus 2CL. So this and this is cancelled. So CD naught is equal to CL square by pi E aspect ratio E. So we will get here that this CL is equal to under root CD naught plus pi E aspect ratio. We can write this under root CD naught by K. So we got this relation that CL is equal to under root CD naught K for a maximum value. So for a CL maximum, you have to put CD naught, CL by CD maximum, CD naught by K we have to put. Now for a maximum CL, revisiting that L is equal to W minus TR sin alpha T and CL is equal to L by half rho V square SW. We can write here L is equal to W minus TR sin alpha divided by half rho V square SW. Here we can write W minus for TR sin alpha T. We can write W by L by D cos alpha T plus sin alpha T divided by half rho V square SW, because here TR is equal to W by L by D cos alpha T plus sin alpha T. We have put this value for the TR. Now the simplifying this equation, we will get CL is equal to W by half rho V square SW 1 by 1 plus D by L tan alpha T. This is the final expression for the CL. So this is the expression which we have find out. Further we will go for CL is equal to W half rho V square SW 1 upon 1 plus 1 by L by D maximum tan alpha T is equal to, this will be CD, which we have seen, pi E aspect ratio. So we can find out that CL is equal to under root CD pi E aspect ratio or under root CD naught by K. This is the CL. So minimum drag speed. So how to find out the minimum drag speed? So minimum drag speed we can find out from the previous equation that under root 2 by root 1 by 4 pi e aspect ratio under root w by sw by rho whole under root 1 by 1 plus 2 under root CD naught by pi e aspect ratio plus CD naught L into tan alpha. Just we have put this value for the under CL alpha. So this is the velocity for a minimum drag speed with thrust angle alpha t is not equal to 0. Now we will find out the power required to maintain steady level flight. Power required is written as PR is equal to TR into V cos alpha t. For alpha t is small, so alpha t is equal to 0. So this we can make as a 1. So PR is equal to TR into V and TR is equal to drag. TR is equal to drag for steady and level flight. So PR is equal to dV for steady and the level flight as TR is equal to D. Now we have to find the expression for power required with respect to the known parameters. We have to find out the velocity. V is a function of the CL. So V is a function of CL. So we can write the CL is equal to half W half rho V square SW. So V is equal to under root 2W by SW SCL. So this is the velocity equation. Now I will go for the derivation of PR, power required. So we know that power required is equal to thrust required into velocity. Thrust required into velocity we have find out 2 into W by SW rho CL. TR we can write the drag 2W by S rho CL because TR is equal to drag. We have to derive that. Now TR is equal to CD by CL into W, W by CL by CD or W by L by D. So now we can put here that CD by CL into W. We know that CD is equal to CD naught by CL plus CD naught by into L plus CL by pi E AR into W. Putting this equation in the equation number 1, that dV is equal to PR. Equation number we have find out that dV is equal to PR. So PR is equal to D. So D we can put this value from here. CD naught by CL plus CD naught L plus CL by pi E aspect ratio into W. And for the V we can put whole under root 2 W by SW by rho. So now CD naught by CL plus CD naught L CL by E aspect ratio. This 2 we have taken outside under root 2 into W under root W by SW by rho into here it should be CL, and this CL has 1 by under root 1 by CL. Now we will see that PR is equal to under root 2 CD naught by CL to the power 3 by 2 plus CD naught L by CL to the power 1 by 2. We have multiplied 1 by CL, CL to the power 1 by 2 pi E aspect ratio under root W by SW by rho into W. Putting CL is equal to W by half rho V square SW. We are putting here everywhere. So we will get PR is equal to CD naught rho V cube by 2 W by SW plus CD naught L into V plus 2 W by SW divided by pi E aspect ratio rho V into W. This is the final expression for the power required, and this power required will vary with the altitude. If you see here, rho is here, rho is here. So as you increase the altitude, your power required will be also increasing. As you increase P1, minimum is here, then minimum is here. So your this velocity will be also increasing and your power required will be also increasing. So as you go high and high altitude, your power required will be high and your minimum velocity will be also high. These are the references. Anderson JD Aircraft Performance and Design International Edition, McGraw Hill's first edition 1999. SL by ME Aircraft Performance Theory and the Practice AIA Education Series. Any questions, you are welcome to ask. My email ID ydwedi@gmail.com. Please do like and subscribe. Be tuned for my next lecture. Very soon I am going to take the next lecture. Till then, goodbye. See you. Thank you very much for the joining.
Like, share and subscribe. Hit the bell icon for more updates.